This presentation is delivered by the Stanford Center for Professional Development.
Hey everyone, welcome. I actually have one hand up free today, and Ryan just walked in with it, so he's going to be passing it around to the people who are in the room. Remember, we have a special discussion section today at, I'm forgetting what time it is. What did I say, 1:15? I have to check. Whatever I said on Wednesday. What did I say? 2:15. Okay, I don't know why I'm forgetting. 2:15 to 3:05 in Skilling 191. We're having a special discussion section just this 1 week because I want some example problems to sit in front of you and for you to think about them more than 2 days before the next assignment deadline, which is why I'm having it today. It's going to be videotaped. I'm going to actually call SCPD after lecture today and try and make sure that they post it by 5 o'clock today so it's around for the weekend online so you can watch it. But I've already, I think, pretty well advertised that assignment 4, I think, to be kind of the biggest surprise in terms of workload and difficulty for most students. So that's why I'm kind of advertising it now to be something you want to start on sooner than later. Because if you start next Thursday, it's very likely you will not finish on time. So just try and take a stab at it a little bit ahead of time this time. When I left you last time, I had shown you two examples of how function call and return works in general, but specifically in our assembly language. So what I want to do is I want to do one specific example, actually much even simpler than the last example I did, because I want to make a transition from C code generation to C++ code generation and show you just how similar the two languages ultimately end up looking like when they compile to assembly code. So let's deal with this scenario. A void function. I just want to say foo, and I'll concern myself with the allocation of two local variables. I'll set x equal to 11, I'll set y equal to 17, and then I'm going to call this swap function. This time I'm interested in writing swap to show you what the assembly code looks like. And I think you'll be surprised to see how the pointer version of swap and the reference version of swap look exactly the same. But the way I'm writing it right now, this is pure C code. Actually, you can call it C++ code for that matter. And then that's all I want to do. I just want you to understand how code for this would be generated. I don't have any parameters whatsoever. So I would expect the stack pointer right there, to have the safe PC associated with whatever function happens to be calling foo right here. There's a call foo instruction in someone else's assembly stream, and that safe PC is the address of the instruction that comes directly after that. That's the trail of popcorn I was talking about on Wednesday. The first thing that'll happen is that this thing will actually make space for its two locals. I actually like getting in the habit of kind of taking care of my deallocation call right away. That makes sense to people? Okay. Well, as soon as I write that, I just want to remember, just so I don't forget to put it on the page, to put the balancing SP change at the bottom of the stream. Now I'll concern myself with this right here. This brings this down to introduce those 8 bytes. X is above Y. So this instruction right there translates to m of sp plus 4 is equal to 11. Then m of sp is equal to 17. And then virtually all of the rest is associated with the work that's necessary to set up and react to, set up a function call and react to its return. Okay? So what I want to do here is I want to evaluate ampersand of x and ampersand of y. The fact that there is an 11 here, whoops, an 11 there and a 17 is really immaterial to the evaluation of these two things right here. This, given that setup right there, is synonymous with PC plus 4. This is synonymous with PC. Okay, I want to put those values in registers. R1 is equal to SP. I'm sorry, that's right. SP. R2 is equal to SP plus 4. This is ampersand of Y. This is ampersand of X. I want to further decrement the stack pointer by -8. The fact that this is -8 is just a coincidence with that being -8. There happened to be two 4-byte parameters being passed here. There were two 4-byte parameters, two 4-byte locals local to foo. Once I've done that, I've decremented this by 4 more bytes. That marks the bottom of the foo activation record. I'm now building a partial activation record for the swap function. I want to lay this as a figure right there. This as a figure right there. This first parameter, the 0th parameter, actually goes at the bottom. So I want to do this. M of SP, what's just changed, is equal to R2. M of SP plus 4 is equal to R1. Okay? That basically gets this right here to point to that, and this to point to that. So when we go ahead and call this swap function, we're just inferring its prototype to take 2 int stars. It just sees this. Technically, it has the addresses, the locations of the 2 ints it's going to be dealing with, but it doesn't technically know that they're right above it on the stack frame. It actually just has the addresses on their little houses that happen to be just down the block. Okay? This right here, all it has to do is basically clean up the parameters. When the call swap function happens, PC is pointing right there. It can, by protocol, assume that that's where the safe PC is left. I'm sorry, the stack pointer is left when it jumps back to this instruction, because the return at the end of the swap is responsible for bringing it all the way back up here, just by protocol. Does that make sense? Okay. So all I need to do, fill in the space. This balances that, that balances that. You could coalesce these to one statement if you wanted to. I just don't see a compelling reason to. And then, since there's nothing being done with the new values of x and y, I can just return. Okay? Does that make sense to people? As far as the code for swap is concerned, this is a void swap. I'll write it to be int star specific. AP int star BP int temp is equal to asterisk AP. There's actually a little bit of work here at the assembly code level. I know you've seen this implementation probably 40 times in the last 2 quarters, but there's some value in actually seeing it one final time and for me to generate assembly code for it. It starts executing with the assumption that SP is pointing to a saved PC. In this particular example, it happens to be that address right there. That's the saved PC. This is internally referred to as AP, BP. It's not like the words AP and BP are written on the hardware, but there's just the code is generated in such a way that AP is always synonymous at the moment with SP plus 4, and BP is synonymous with SP plus 8. Okay? The moment the stack pointer points right there, I have to make space for my one local variable. That happens because I do this. I'll make it clear that this is associated with the label swap that we actually call or jump to. That brings this down here. This is locally referred to as temp in the code. This is the space that corresponds to temp in the activation record. The offsets of AP and BP actually shift a little bit. Now this is at address SP plus 8, SP plus 12. I have to rely on these things pointing to real data. I don't need to know where that data is to write the correct assembly code. I need to evaluate AP and then what AP points to. So as part of initializing that right there, I have to load into a register M of SP plus 8. Do you understand that it lifts this bit pattern right there and places it in a register? So I can basically do a cascade of dereferences. Does that make sense to people? Okay. Now I have AP in a register. I can do this. And now I have the very integer that is addressed by this AP thing, okay, sitting inside R2. You may ask whether or not you can do something like this. Conceptually, of course you can do that, except you're not going to find an architecture that supports a double cascade in a single assembly code instruction. Okay, so that's why they're broken up over several lines. So let's assume that this points to that right there. That's the integer that has to be loaded into temp. That's only going to happen because I do this. Whoops. And that ends with this line right here. Does that make sense to people? Yeah, go ahead.
When you say R2 equals M, R1,
Right.
why does it not just copy the address inside AP and actually dereference it?
Well, the memory of, you basically go inside an array of bytes that's base addressed right there. Okay, so you think about the entire array of bytes that's in RAM as being indexed from position 0, and so when you put that number inside, it actually goes to that address. We know that SP plus 8, this right here, we know that the 4-byte bit pattern that resides there is actually the raw address of some integer. The assembly code doesn't know that, but we do. So we're asking it to shovel around a 4-byte figure and put it into this temp variable, right? This loads that address. This address right here, let's say it's address 4000. I just loaded a 4000 into R1. Maybe it's the case that the 17 is at address 4000. Okay, that would make sense. So by effectively doing M of R1, in this particular case, I'm doing M of 4000 because that's what R1 evaluates to. Okay, and by default, we always do with 4-byte transfers. Okay, so this would get a 17 to play the role of happy face and would put a 17 right there. Does that make sense? Okay. So now what has to happen is something similar. I have to do this right here, but it's actually a little different than this line right here because I have to find the L value by actually following a pointer. The L value being temp is directly on the stack frame in this case, right? The space where the new value is being written is actually one hop off of the stack frame. Okay. Let me evaluate asterisk BP first because it's very similar. I will do R1 is equal to M of SP plus 12. That loads just the value of BP because that's what's stored as a variable on the stack frame. Okay. In R2, I'll do M of R1, but R1 has a different value this time. Maybe it is the flat emoticon. Okay, and that gets loaded into the R2 register. That's what actually has to be written over this smiley face right there. Make sense? So in order for that to happen, I have to load this again. R3 is equal to M of SP plus 8. And I don't want to load M of R3 because I don't care about the old value. I want to actually set M of R3 equal to R2. Okay? Does that sit well with everybody? Just making sure I did that right. Yeah, AP right there. Okay? Make a sense? The last line is actually very similar to the first one. I know that temp is sitting right at the base of the entire activation record. Now what I have to do is I have to load the address associated with BP into R2. That's stored at M of SP plus 12. And then I have to do M of R2. M of R2 is equal to R1. That realizes this right here. So in those 3 blocks, I've achieved the algorithm that is the rotation of these 2 byte patterns actually through a third. Right before I finish up here, I have to do an SP is equal to SP plus 4. Internally, I have to bring the stack pointer up to the place where it was before I executed any code for this function. Okay? That means that SP is now pointing to the safe PC, which is perfect because in response to this return instruction, our return actually knows just procedurally to go ahead and pull that value out, populate it with place it into the real PC register, and simultaneously, or just after that, bring this back up to there. Okay? That's exactly where the SP pointer was pointing before that call statement. Does that make sense? Okay. So I went through that exhaustively because pointers are still mysterious for some people, and understandably because they're difficult. So if you start to understand them at the hardware level, you have some idea as to what the pointers are trying to achieve. They really are raw locations of figures being moved around, or at least manipulated. Okay? What I want to do now is I want to show you what the activation record and the function call and return mechanisms would be for the C++ version of SWAP. This is very close. I'll write it again and leave it as an open question for about 2 minutes as to what the activation record must look like. I'll just do A, int, ampersand, B. So just pretend that we're dealing with pure C, except that we've integrated the reference feature from C++. Okay? Int temp is equal to, what did I say over there? A. Then A is equal to B. And then the B is equal to temp. Algorithmically, it looks similar, and it even sort of has the same side effect. But you may question how things are actually working behind the scenes in order to swap things by reference as opposed to by exposed address. Let me draw the activation record for you. This is the thing that's referred to as A. This is the thing that's referred to as B. This is always below that. That's just the rule for parameters to a function or a method call. There's a save PC right here, pointing to the instruction that comes right after the call to the swap function. And then ultimately, the very first instruction does an SP is equal to SP minus 4, so that this is the entire activation record that is in place before swap actually does anything in terms of byte moving around. Okay? This A and this B, just because we refer to them as if they're direct integers, doesn't mean that behind the scenes they have to actually be real integers. The way the way references work is that they are basically just automatically dereferenced pointers. Okay? So, without writing assembly code for this, when I do this, and I do this, just because I'm passing in x and y, that's the way you're familiar with the swap function from 106b and 106x, just because you're not putting the ampersands in front of those x's and y's doesn't mean the compiler is blocked from passing their addresses. This right here has to be an L value. This has to be an L value as well. It means it actually has to name a space in memory, okay, that can be involved in an update or an exchange by reference. When this right here is compiled to CS107 assembly language, it actually does exactly the same thing that does right there. C++ would say, oh, this is x and y, but I'm not supposed to evaluate x and y because I can tell from the prototype that they're being evaluated, they're being passed by reference. So the way it does it is it, on your behalf, just secretly, says, okay, they really need this x and this y to be updated in response to the swap call. That's only going to happen if this as a function knows where x and y are. Okay? So the illusion is that A and B, as standalone integers, are second names for what was originally referred to as x and y. Behind the scenes, what happens is that this lays down a pointer, and this lays down a pointer. You don't have to use the word pointer to understand references. You can just say it's magic, and somehow it actually does update the original values. It lays down the address of these things. The assembly code that is generated for this function right here understands, even though you don't necessarily know this, it understands that it's passing around pointers wherever references are expected. And so it automatically does the dereferencing of the raw pointers that implement those references for you. The assembly code for this function is exactly the same as this. Like down to the instruction, down to the offsets, everything is exactly the same. Okay? Do you understand how that's possible? Just because you don't put ampersands in there doesn't leave the compiler clueless, because it knows that from the prototype that it's expecting references. It's just this second flavor of actually passing things around by address. You're just not required to deal with the ampersands and the asterisks. Okay? It knows, because of the way you declared these, that every time you refer to A and B in the code, that you're really referring to whatever's accessible from the address that's stored inside the space for A. Okay? Does that sit well with everybody? Okay, that's good. So people freaked out a little bit on assignment 1, I think, or assignment 2, when they saw local variables declared as references. Like, you're used to the whole parameter being a reference, as if this data type and that data type, that you're only allowed to put them in parameter lists. That's just not true. If you want to do this, if you do this right here, then that's just traditional allocation of a second variable that happens to be initialized to the x variable, or I'm sorry, to whatever x evaluates to. Okay, and that's just normal. If you want to do this, you can. Okay, and this isn't a very compelling reason, because ints are small and there's no real algorithm attached to this code, so you're not necessarily clear why I would do that. The way this is set up is that x really is set aside as an integer with a 17, y is really set aside with its own copy of the 17, but z is declared. You drew them in 106b and 106x this way, and the picture is totally relevant to the actual compilation measures, because it really does associate the address of y inside the space that's set aside for z. Okay? Does that make sense? If I were to do this, you would totally draw that without the shaded box, right? This and this, from an assembly code standpoint, are precisely the same. At the C and C++ language level, you're required to put the explicit asterisk in here. You're not there. Okay? You may say, well, why would I ever use actual pointers if references just become pointers? Well, references are convenient in the sense that they give the illusion of second names for original figures that are declared elsewhere. The thing is, with references, you can't rebind the references to new L values. Do you understand what I mean when I say that? It's a technical way of saying you can't reassociate Z with X as opposed to Y. Once it's bound as a reference to another space, that's in place forever. So you don't have the flexibility to change what the arrow, where the arrow points to. You do have that ability with raw pointers. So you could not very easily build a linked list if you just had references. Does that make sense to people? Okay, so that's why the pointer still has utility even in C++. Okay. You saw a method where, I think it was like getLastPlayer or something like that. There was some method in one of the classes for assignments 1 and 2 that returned a reference. And people were like, I've never seen that before. What does that mean? All it's doing is it's returning a pointer behind the scenes, okay? And you don't have to deal with it that way. You can just actually assume that it's returning a real string as opposed to a string star, or an int as opposed to an int star, and just deal with it like that. But behind the scenes, it's really referring to an int or a string that resides elsewhere. Does that make sense to people? Yes, no? Okay. So even though in C, when you C++, you start dealing with references, it's not like the compilation efforts that are in place. And the assembly code that's generated is fundamentally different in the way it supports function call and return and just code execution. Okay? It just has a different language semantic at the C++ level that happens to be realized similarly at the assembly code level. Okay? References are the one addition to C++. No, I'm sorry, there's a few, but there are a lot of people, when they program in C++, they actually program in C, where they just happen to use objects and references. They don't use inheritance. They don't necessarily use templates all that often, although most of the time they do, but that's not an object-oriented issue. They don't use inheritance. They don't use a lot of the clever little C++isms that happen to be in there. They really just code in C with references and objects. And they just think of references as more convenient pointers, less confusing, and they think of objects